All right, let's just dive right into this explainer. We're breaking down the highly anticipated Gemma 4 technical report. This thing just dropped on Hugging Face, submitted by Omar Sensiviero on July 8th, and man, it is already sending absolute shockwaves through the developer community. We're looking at a brand new generation of open-weight, natively multimodal language models straight from Google. And honestly, the technical choices they made here are they're absolutely fascinating. So whether you're out there building next-gen AI agents, or you just want to get a grip on where frontier models are heading, this is exactly the info you need to know.
Okay, here's our quick roadmap to unpack this whole paper. First, we'll meet Gemma 4. Second, we'll look at the architectures and scale. Third, we'll dive into the 12B encoder-free anomaly. Fourth, we're going to enter thinking mode. And finally, number 5, we'll weigh the rapid adoption against the community critique.
Let's kick things off with Section 1. Meet Gemma 4, Google's multimodal leap.
So, to really set the stage and establish the sheer scale right away, you got to understand that this model family covers an incredibly wide spectrum. On one end, we've got a highly compact 2.3 billion parameter model. Think of this as your lightweight architecture, the kind designed specifically for efficiency and edge case deployment. But then on the exact opposite end, we scale all the way up to this massive 31 billion parameter flagship model. This massive spread, it basically tells us Google isn't just aiming for a single niche use case. No, they are completely blanketing the ecosystem. They're providing natively multimodal models, which, by the way, just means they inherently understand different types of data, like text, image, and audio, across literally every conceivable compute budget.
Moving right along to Section 2, Architectures and Scale, specifically dense and MOE. Right in the abstract, it points out that Gemma 4 is designed to drastically advance compute efficiency by utilizing two distinct frameworks. We have your standard dense architectures and then something called Mixture of Experts, or MO for short. Let's demystify that AI jargon for a second. An MOE system basically means the model selectively uses its brain power based on whatever prompt you give it. Instead of, firing up every single parameter for a super simple question, it smartly routes the task to specific neural expert pathways. So why should you even care about that? Well, because this incredible efficiency is exactly what helps Gemma 4 achieve a major leap in performance across really complex STEM subjects and long context benchmarks. And it does all of that while keeping memory usage and inference speed highly optimized. It's a real game changer. Which brings us to Section 3, the 12B encoder-free anomaly, or as I like to call it, a unified maverick.
Now, the 12 billion parameter model acts as the absolute maverick of the Gemma 4 family. It's so interesting. If you look at the technical specs across the board, Google upgraded the vision and audio encoders for all the other model sizes. The 2.3B, the massive 31B, they all get these shiny new dedicated encoders to process sights and sounds. Well, all of them except for one, the 12B. For this specific size, Google proposed something radically different. They went with a unified, entirely encoder-free architecture.
And the way this Maverick approach actually works is brilliant. Instead of passing audio or visuals through a separate translation layer, an encoder, the 12B just bypasses traditional encoding steps entirely. Here's how it flows. Step 1, it ingests raw audio directly. Step 2, it ingests raw image patches directly. And Step 3, it processes this multimodality in one single unified workflow, without any of those dedicated encoder bottlenecks. Actually, it's a fascinating structural experiment sitting right smack in the middle of their model lineup. It directly challenges the whole assumption that we strictly need separate encoders for multimodal understanding.
Moving on to Section 4, Enter Thinking Mode, which is all about generating reasoning traces.
I've got to say, this is arguably the most futuristic feature integrated into this entirely new model suite. Letting the abstract speak for itself here, the authors state they integrated a mode enabling Gemma models to, quote, generate reasoning traces prior to responding. Okay, what does that actually mean for us? It means the model can effectively think out loud. Before it just spits out an answer to a complex prompt, it builds a visible logic chain. It actually works through the problem step by step internally. And the paper notes that this process helps these models rival much larger, frontier open models when it comes to human-rated tasks. It's not just regurgitating or retrieving information anymore, it is literally reasoning through it.
And that leads us to our final part, Section 5, Adoption versus Critique, where hype meets reality. So, with all these incredible architectural leaps we just talked about, how did the open source developer community actually receive this release? Well, the immediate adoption metrics were just absolutely staggering. Within days, literally days, of the paper going live, we saw massive traction over on Hugging Face. We're talking 979 different spaces citing this paper. And these aren't just empty links. These are real-time functioning demos, including a real-time voice agent and totally new vision workflows like the Gemma avatar and the Crea 2 LoRa trainer. Add to that 40 different models explicitly citing and integrating this tech, plus 53 upvotes on the paper itself. It is super clear. The market absolutely wants this capability, and they are rapidly deploying it.
But we have to objectively contrast those massive adoption numbers with some really sharp, highly upvoted community critique that popped up right in the comments section. For instance, Hugging Face user Shadow Lilac directly pointed out a pretty frustrating lack of scientific transparency. They wrote, quote, almost no disclosure of any detail, unlike Gemma 3's technical report, and instead, standard well-known procedures were simply explained with almost no input, ablation, negative findings, positive findings, scaling laws, end quote. This really hits the nail on the head regarding a major friction point. The community was fully expecting the rigorous, deep academic breakdown they got with previous iterations, but instead, they got what some view as kind of just a high-level summary.
So the crucial takeaway here is this intense, real-time tension between hype and reality. On one side of the scale, we're seeing massive commercial-scale adoption. Developers are just rushing to use these highly capable, natively multimodal models to build some truly incredible tools. But then, right on the other side, we have the strict, deeply held expectations of the open-source developer community. They demand transparent disclosures, things like scaling laws and ablations, to truly fundamentally understand how these models were built in the first place.
As the industry pushes the absolute boundaries of multimodal capabilities, and as they introduce advanced features like thinking modes, we're really left standing at a crossroads. We have to ask ourselves, will future open-weight releases just continue to sacrifice deep scientific disclosure for raw performance and rapid market adoption? Or will the heavy pushback from the open-source community force a return to rigorous, transparent technical reporting? Honestly, it's a fascinating dynamic, and we'll definitely be watching it unfold. Thanks so much for joining me on this explainer, and I highly recommend diving into the source material on Hugging Face to see these models in action for yourself.